Okay, so here's part 2 and 3. Notice this time we're going to be solving an equation, and this time I have the left side is still the 3x minus 2, but the right side instead of 0 is now a number other than 0. So what about a situation like this? Well, same idea. This equation right here and this one right here, and we're looking for the x value that satisfies both of these. What x value do I put in here that's going to give me the 10? That's what we're doing. In a numerical table, same process. This one is just a single number, so we're looking for the y values that produce an x value that produces the y value of 10. Pick some numbers to plug in here. It doesn't matter which ones I pick. If I start at 0, I will get -2, and if I start at 1, I will get 1. Establishing our slope, which we already know to be 3. The change in the y values. So this from here to here is going to be +3. From here to here is +1. So my change in x's is 1. So I need to find when this is going to be a 10. So from 1 to 10, this is a +9. So if it's +9, that means I did 3 of these. Because 3 times 3 is 9. So then it means I need to do 3 of these. So that'd be +3 up there. 1 plus 3 is 4. So numerically, we've established our solution to be when x equals 4. Would be our solution. That is the value of x that will produce a 10 in here. And thereby equaling that. Let's look at a graphical solution. So in this sense, we're going to graph the numbers that I have and what I have going on here. This time in my equation, I have y equals 10. So that is a horizontal line at 10. So let's establish that line. When it was 0, it was on the x-axis. Now it's up here. This is y equals 10. And we're looking to see where this line crosses this line. So we have our table here. 0, -2, which is right about here. And then we have the point 1, 1, which is right about here. A little bit harder to do this because of the scaling. Okay, but if we draw this out, it should still work. If I have everything lined up, we line it up better. And if I draw my line, so this is the line y equals 3x minus 2. And you can see that right here at 4, when x is 4, the y is 10, which is what I'm looking for, that point of intersection. And there again, confirming that I have a solution of x equals 4. So what about algebraically? Algebraically, we're still doing the same thing we did before. We have an equation. That means this is in balance. I'm trying to get to the x. So I have to undo the operations that are being acted upon x. If I put a number in for x, I would first multiply by 3 and then subtract 2. So I need to do the exact opposite of that, which means I need to remove the -2 first. To do so, you can add the opposite, which is the better way to think of it. Some people just add 2. So put a +2, the opposite of subtracting 2, on both sides. You got to do it to both sides of the equation to keep it in balance. You cannot unbalance an equal sign. Going straight down in column format, I have a 3x. That will be a 0 equals, and that will be a 12. To undo the timesing by 3, again, my recommendation is to think of it as we want to make this into a single x, 1x, to, most people will say, well, divide by 3, and you can. I like to multiply both sides by the reciprocal. That means I can do mine in 1 step, where some people do it in 2. 1/3 of 3 is 1, which is what I wanted. 1/3 of 12 is 4, and thereby confirming our solution. And again, remember, once you have a solution in the graphical sense, our graph right here, if I condense all this down onto the x-axis, it will produce a single line graph. So here would be 0, here would be 4, and the dot would be on 4 because that's where the solution is occurring at 4. Okay, so this is the single line, a single number line graph, and it's important. I'm showing you this because we're going to be using it in a later date. So see how this is happening, and everything I'll show you on the single number line makes a lot more sense to it. So that's the part 2.1 where we had a different number other than 0. Here's the part 3 version, a little bit more advanced. In this case, we're going to solve this one. But once you understand the concept of what's happening, we just keep extending this out. So again, like in the ones we did before, when is this side, y equals 3x plus 1, going to match y equals 7 plus 5x? When are these two lines going to intersect? We want the same x and y value for both. So make a table for both. So this line I'll put over here. And again, we can establish some values. Start with 0, start with 1. Okay? And then we can do, and then this one over here. So what I would recommend in a situation like this for numerical is just plug in the same values. Plug in 0 and then 1. Okay, if I plug in 0 for this one, I'm going to get 7. If I plug in 1 in here, I'll get a 12. And we can establish our slope and rate of change. We already know the slope of this one is going to be 3. So this is plus 3, plus 1. So my slope here, my change in y's is 3. My change in x is 1. Continuing that process over here, add 3 to this, I'll get a 7. Add 1 to this, I'll get a 2. And you'll notice something interesting right here. This one right here is 5. 1. Add 5 to this. Add 1 to this. And you'll notice, like right here, both y values are 7. But don't fall into that trap. I'm looking for the point where these two things will intersect at. They have the same y value, but notice the x values are different. So these are not our solutions. Okay? Over here, we can see that the slope for this one is 5. So this one is increasing fairly quickly compared to this one, the slope of 3. And so at 2, this answer is 17. This answer is a 7. And this one is just going to keep getting bigger faster. So it's never going to intersect there. So that means the point where they're going to intersect has to be in the negative sense. So doing that, let's go back and look at the table in a negative direction. So take this right here. We'll start, here's the 0, 1. And we have a rate of change going that way of 3. So if I go backwards, minus 3, minus 1, this would be negative 1, minus 3. And do another minus 3 here. Actually, let's do it this way. What I did here is I subtracted 6 because I'm trying to get to, and I'll show it to you because I'm running out of time. That right there. So I just did it twice. And then this one over here, here's the 0, 7, and minus 5, minus 1. And then minus 10, minus 2. This gives me the negative 8, and this gives me the negative 3. And we can see that we have the solution right there. So we know that our solution is going to be when x equals negative 3 from the numerical sense. Now, just so you know, I will never ask you to do the table approach on a test. It's very challenging, as you can see. You kind of know what you're doing, and it can take some time. So on the test, when I have this one right here, you would just be asked to do the numerical I'm sorry, the algebraic and the graphical. So let's look at the graphical. We have a table established. We're going to graph both lines on the same axes. We'll see what happens where they cross. So I'm going to graph the first one here. I have 0, 1. Let me make sure I can see it. So we're going to graph that table right there at 0, 1. And then another point's at 1, 4. And we can even graph the 2, 7 so you can see it. Ignore this piece, it was from the previous graph. And so here is that first line. And so line everything up as neatly as possible. The more accurate you are, the better your graphs will look. And you'll see where they cross. If you are sloppy in your graphs, you won't see the point of intersection. So this is the line, y equals 3x plus 1. Let's do the other table. The table had a 0, 7. Okay. And then it has a 1, 12, but I'm not going to be able to get to that one because I can't go up high enough. So let's graph one of these other ones I did. How about negative 1, 2. And if I connect those dots, you will see that they are going to cross right down here at negative 3, negative 8. And this is the line 7 plus 5x. So that point right there, again, shows that the answer is when x equals negative 3 is where the lines are going to cross, establishing our solution. Our single number line solution then, here is 0, 1, 2, 3, negative 3, and a dot right there. That's what it would look like. So the only left here is the algebraic approach. So we have 3x plus 1 is 7 plus 5x. So now I have two terms, two values that have an x in it, one on each side. And our goal again, as always, is to get x equals. So I need to first start off by getting these x's together. And just like the technique from before, to get something from one side, you need to add the opposite of it. So I usually move the smallest one. Since this is smaller than 5x, I'm going to add a negative 3x to both sides. And notice that I'm lining them up along the like terms. Add in column format. That will be 0 plus 1 equals 7. And then 2 plus a negative 3 is a plus 2x. And so now you can see that I have a single x term over here. We want to get x by itself, so just like we did in the previous problems, the opposite of adding 7 is to add a negative 7 to both sides. Column form, there's a negative 6 equals, that is gone. This is 2 and x. Putting both sides in parentheses, we're going to add by the reciprocal, multiply by the reciprocal, 1/2. 1/2. I established that x is indeed equal to negative 3. And it is okay to write it this way. This is the same answer as that up there. So this is an algebraic response. And then we saw a graphical response. For, again, one of these types like this, I will not have you do the numerical approach, but it is there. And this is the stuff I want you to see how everything is connected between graphing and solving and how you can find solutions in many different ways.